Good afternoon, class. I hope you are all having fantastic days. So in this video lecture, we are going to cover chapters 3 and 4. This should all be review from previous statistics classes that you have had. I'm simply going to summarize chapters 3 and 4 to bring you up to speed, help you remember some of the things that you may have forgotten, and to make sure that we're all on the same page. So chapters 3 and 4 are really about random variables. Random variable is defined in chapter 2, and a random variable is a real valued function assigning a numerical value to each possible outcome of an experiment. So long story short, we have some sort of random outcome. It's not necessarily numerical in nature. It could be heads or tails. And then based on the outcome of that experiment, we assign a value to each possible outcome. So we might, for example, assign the value 0 to a tail and a value 1 to a head. And in terms of notation, it's very important to recognize the difference between uppercase and lowercase letters. So in this class, when we use uppercase letters like X and Y, those are going to denote random variables. They're not actual numbers. They are really an idea. They are something that is going to take a numerical value based on some random experiment. Lowercase letters, on the other hand, such as lowercase x and lowercase y, will denote a particular value that a random variable may assume. So suppose you roll two six-sided die and you sum the number of dots on the faces pointing upward. Let y denote the value of this sum. Then in that case, y is going to be a random variable with possible values 2, 3, 4, all the way up through 12. And so we have a random experiment. We're rolling two die. The outcomes are the number of spots or dots that are facing upward after we roll the two die, and the variable, the function, simply takes the number of dots, adds them together, and that's going to be our random variable. Related to a random variable is something called the cumulative distribution function, which is going to be abbreviated CDF. And the CDF of a random variable y, which is denoted by capital F taking the argument lowercase y, is a function that is defined as the probability that our random variable is less than or equal to the value of lowercase y. So capital F denotes the CDF. It takes the argument lowercase y, and that indicates the upper bound for the values of y, the values of the random variable that we are interested in. And when it's important to distinguish between more than one random variable, then we might denote the CDFs by F of subscript y, which denotes that this is in fact the CDF for the y random variable, and if we had another variable x, we might denote the CDF by F of x and then taking the argument little x. And so if we need to distinguish between the different random variables, then we can do that using the subscripts. And the CDF has various properties. These are things that can be proved using set theory fairly easily. So for the properties that are useful to know are that a CDF has the following properties. So one is that as we let lowercase y go to negative infinity, the value of the CDF is equal to 0. And basically this is saying that the value of y, the probability that our random variable has a value smaller than negative infinity is equal to 0. Which of course makes absolute sense. Nothing can be smaller than negative infinity. It's not even a real number, but the probability that we have an outcome that is smaller than negative infinity is of course 0. It's not possible. On the other hand, if we let lowercase y go to positive infinity, then the limit of the CDF as y goes to positive infinity is equal to 1. In other words, the probability that our random variable takes a value less than or equal to less than negative infinity has to equal 1. So any possible outcome has to be less than positive infinity. Another property of the CDF is that it is a non-decreasing function. So if lowercase y1 is less than lowercase y2, then the value of the CDF evaluated at y1 has to be less than or equal to the CDF evaluated at y2, simply because this event or this probability contains more possible outcomes. Another way of saying that, so using set theory just to make this completely obvious, if A is equal to to the events that y is less than or equal to y1, and b is equal to the events that y is greater than y1 and less than or equal to y2, then the probability, well, I should say, the CDF evaluated at y1, which is the probability that the random variable y is less than or equal to y1, is just the probability of A, and that has to be less than or equal to the probability of A union B, which is the probability that y is less than or equal to y2, which is f of y2. So in fact, the CDF is a non-decreasing function. And the last property, in this theorem at least, is that the CDF is a right continuous function. So if you're looking at the value of the CDF as, so if we're looking at the value of the CDF at y plus epsilon, as epsilon goes down towards 0, that's going to be equal to f of y. And so if there are jumps in our CDF function, which is certainly possible, then the holes are on the left side, not on the right side. So in other words, what that means is that if I were drawing a graph of my CDF function, it's certainly possible that I could have a hole where my CDF jumps. And if in fact that is the case, then if I'm traveling left along my x-axis, then that's going to be continuous with the value the CDF actually takes, and then if there's going to be a jump, it's going to be coming from the right-hand side. So if we were coming from this side, when we get to this point, there's a jump. And so it's not continuous going from the right-hand side, but it is continuous going from the left-hand side. So some basic definitions related to random variables. So a random variable y is discrete if it can only assume a finite or a countably infinite number of distinct values. So if a random variable is discrete, or if a random variable has a finite number of values, then it's certainly discrete. But even if it has countably infinite, it's still going to be discrete. So an example of this is the Poisson distribution, which we'll talk about later, which can take the value 0, 1, 2, all the way up to infinity. It's countably infinite, so it's going to be discrete. And oftentimes, discrete random variable has a count of some sort. So for example, the number of times my heart beats in a day, the number of children a couple has. If we count something, it's going to be a discrete random variable. And a function related to discrete random variables is the probability mass function, or PMF. And the PMF of a random variable y is denoted by lowercase p of y, and it's defined to be the probability that the random variable takes the specific value of y. So because a discrete random variable takes a countably infinite number of values, we can actually talk about the probability that it equals a specific value with in a sensible way. And there are some properties related to the PMF function, the probability mass function. All values of the PMF have to take values between 0 and 1. And this should be obvious simply because this is a probability. All probabilities are between 0 and 1. And because of that, the PMF function has to take values between 0 and 1. Additionally, if we add up all the PMFs for all possible values of y, it has to be equal to 1. And the reason for this is basically if we add up the probability of all possible events, then they have to add up to 1. And the PMF and the CDF are directly related for a discrete random variable. So if we have a discrete random variable y that has PMF p of y, lowercase p of y, then the CDF is obtained by finding all the values of x that are less than or equal to y, and then adding the probability mass function for all of those values of x. So if, for example, let's say that if y takes the values 0, 1, 2, 3, and 4, and if we wanted to find the CDF evaluated at 2, that could be obtained by adding up the mass function for 0, the mass function for 1, and the probability mass function for 2. And so that's all that formula is saying. And related to the property of the CDF and its relationship to the probability mass function, if you want to find the probability that a discrete random variable is between two values a and b, we once again simply find all the values of y that are between a and b and add up the mass functions, the probability mass functions, for those values of y. So this is all just following the basic rules of probability. The other main kind of random variable is the continuous random variable. And a random variable y is continuous if its CDF, f of y, is continuous for all values between negative infinity and positive infinity. And related to the CDF of a continuous random variable is something called the probability density function, which we'll typically just simply call the PDF. And the PDF of a continuous random variable is simply the derivative of the CDF of the random variable, and it's denoted by lowercase f of y wherever the derivative exists. And it follows that if the CDF is continuous and the derivative exists, then the CDF of that random variable evaluated at lowercase y is simply the integral from negative infinity up to the value of y of the density function. So this is really just a simple property of the fundamental theorem of calculus. So just using one of the basic properties from Calculus 1, if we want to find the CDF of a continuous random variable, and we already have the PDF, the probability density function, we simply need to integrate the probability density function over the appropriate range of values, and that will provide us with our CDF. So the PDF has some properties just like the probability mass function did. So if f of y, lowercase f of y, is the PDF of a continuous random variable, then some of the properties are that the density, the value of the density, evaluated for any possible value of y has to be greater than or equal to 0. There can be no negative densities whatsoever. Additionally, if we integrate from negative infinity to positive infinity, if we integrate our density over the range negative infinity to positive infinity, we have to get 1. So basically, the probability that we have an event has to equal 1. And a theorem related to the property that we saw in the previous slide is that if I want to find the probability that my continuous random variable is between a and b, I simply need to integrate my density function over the appropriate ranges, over the appropriate range of values. Another characteristic of interest related to random variables is the quantile of a random variable. So if we talk about the pth quantile of a random variable, p is going to be a number between 0 and 1, and the pth quantile will be the value of y, the smallest value of our random variable, such that the CDF evaluated at that value of y is greater than or equal to the pth quantile. Related to that is the inverse CDF or quantile function, which is defined or denoted by f inverse of p, and it's the infimum of y's such that p is less than or equal to f of y. So in other words, the inverse or quantile function finds the smallest value of y such that the CDF evaluated at y is greater than or equal to p. So there are some common probability distributions that we use in statistics. So for discrete random variables, some of the common ones are the binomial random variable, the geometric, hypergeometric, negative binomial, Poisson. I'm not really going to introduce any of these in detail. These all should have been things that you learned in your previous statistics class, though I will say that the book does talk about each of these in detail in Chapter 3, so if you have questions, please go there. Some common continuous random variables are the beta random variable, chi-square, exponential, f, gamma, normal, standard normal, t, uniform. There are lots of continuous random variables, there are lots of discrete random variables, but these are some of the most common ones that are used in statistics. And if you have a TI-83 or TI-84, then the PDF, CDF, the quantile functions are all pretty easily obtained in your calculator. Here are some instructions about how you can go about doing this. We're actually not going to talk about that in this class. Like I said, as I said in the syllabus, having this calculator can be helpful to you, but we're going to focus on how to do these calculations directly in R. So to calculate these things in R, what we want to do is determine the appropriate function and arguments that we need to get the function of interest. So, for example, if you wanted to determine the PDF, the density, of a binomial NP random variable, the function that you would use is dbinom. And you would provide it with y, the argument of your density function. Then you provide it with n, the number of trials, and p, the probability of a successful outcome in those trials. If you wanted the CDF of your binomial random variable, you would replace d by p. So d stands for density, p stands for probability, and so p binom is going to be the CDF, f of y, of the same binomial random variable. If, for example, you wanted the density of a normal random variable, then you would use the pnorm function. So the pnorm function, you would supply it with the upper bounds of the CDF that you were interested in. Then you have to supply it with the mean and the standard deviation of your normal random variable, and subtract from that any lower bound that was of interest. If you wanted to find the pth quantile of a normal mu sigma squared random variable, you would use the qnorm function, where you would supply it with the quantile, then also specify the mean and the standard deviation. If you wanted to find probabilities related to the t distribution, you would use the pt function, and you would supply it with the bound of interest as well as the degrees of freedom for the random variable. And if you wanted the quantile of a t random variable, you would use the qt function, where you provide it with the quantile p, and then also nu, the degrees of freedom. And so these are just some examples of the kinds of values that you can obtain pretty easily in R. R has lots and lots of distributions. If you type question mark distributions in R, so let's talk about how to calculate probabilities for some common statistical distributions using R. In this first example, we'll assume that we have a binomial random variable with 10 trials and the probability of success for each trial being equal to 0.3. And we'd like to answer the question, what's the probability that the total number of successes is less than or equal to 3? And the second question is, what is the probability that the total number of successes is greater than or equal to 2 and less than or equal to 6? And what I will say to you is that what you want to do here is you want to write the problem down and then translate it to a problem that is easily solved by R. So pause this lecture, take a few moments, and see if you can't do that yourself, and we'll come back together as a class and make sure we get the correct solution together. Well, I hope you were successful. So let's look at how to do this, this problem in R. So the first thing that we want to do is to write down the probability in question. So for this first example, actually the first thing we want to do is write the information we know. So we know that y has a binomial distribution with n equal to 10 and a probability of success of 0.3. We want to find the probability that y is less than or equal to 4. Well, by definition, that is just the CDF function for the random variable evaluated at 4. And so the appropriate function that we want to use is the p binom function. P stands for probability, which indicates that it's the CDF function, and binom specifies the distribution of interest. So the solution is going to be p binom. We specify the number we want to evaluate our CDF at, which is 4. Size, the argument size, is the number of trials, and then prob is the probability of a success, which in this case is 0.3. So now we can go to R, and we type in, let's clear that, we type in p-binom, so let's just clear the screen here, p-binom 4, size equals 10, prob equals 0.3. And so the probability is pretty close to 0.85. So for the second probability of interest, we wanted to find the probability that y was between 2 and 6 inclusive. And as I previously mentioned, the thing that you really have to do to solve these problems easily using R is translate the initial problem to a problem that's easily solvable using the tools of R. So we want to find the probability that y is between 2 and 6. Well, since it's a binomial random variable, it only takes the possible values 0, 1, 2, 3, all the way up to 10, which means that this probability is actually the exact same probability as the probability that y is greater than 1 and less than or equal to 6, simply because y cannot take any values in between 1 and 2. However, the probability that y is greater than 1 and less than or equal to 6 is the same as the probability that y is less than or equal to 6 minus the probability that y is less than or equal to 1. But now, these individual probabilities are each just the CDF functions evaluated at 6 and 1 respectively. And so we can also answer this question using the p-binom function in R. So we have p-binom of 6, size equals 10, prob equals 0.3, minus p-binom of 1, size equals 10, prob equals 0.3. And so the answer for the second probability is very close to 0.84. An alternative way of answering that second question is that we could actually have added up the individual mass functions for the values of y equal to 2, 3, 4, all the way up to 6. So in other words, this probability is the same thing as the PMF evaluated at 2 plus the PMF evaluated at 3 all the way up to 6. So if we wanted to do it that way in R, so we could type in d-binom. So d stands for density, and it also provides the PMF function if it's a discrete random variable. So d-binom of 2, and by default, R knows that the second argument is size and the third argument is probability, so you don't have to actually write that. You can simply put the numbers in. So we could put 10 and 0.3 plus d-binom of 3, 10 and 0.3, plus d-binom of 4, 10 and 0.3, plus d-binom of 5, 10 and 0.3, plus d-binom of 6, 10 and 0.3. You can see that we get the exact same answer as before. We just solved the problem in a slightly different way. So the second example involves an exponential random variable. So this is a continuous random variable. And our exponential random variable y has scale parameter beta equal to 2, which using the parameterization of the book means that the density is equal to 1/2 e to the negative y over 2, with y taking values between 0 and positive infinity. And the first question we want to answer is what's the probability that y is less than 3? The second is what's the probability that y is between 1 and 3? So I encourage you to once again pause this lecture, see if you can't solve this problem on your own, either using R, or you can actually do this one by hand using integration, and then we'll come back together in a few moments and look at the answer together. Well, I hope that your efforts went well and that you were able to get the correct solution. So let's look at the answer for this particular problem. So the first thing that we're going to do is we're going to state the information that we know. So we know that y has an exponential distribution with beta equal to 2. And for the first problem, we wanted to find out the probability that y is less than 3. And using the definition or the results that we learned in chapters 3 and 4, we know that we can find this by simply integrating the density over the appropriate range, which is starting at negative infinity and going up to positive 3. So we could integrate the density between that range, and you can impress me with your amazing calculus skills by finding the answer. However, even though this is pretty easy to do using standard calculus, we really want to use the tools at our disposal to make our life simpler. So the probability that y is less than 3 is the same as the probability that y is less than 3 plus the probability that y is equal to 3, because for a continuous random variable, the probability that it equals a specific value is always equal to 0. So this is one of the basic rules of continuous probability distributions that I may need to be reminding you of right now. But for a continuous random variable, the probability that the random variable equals a specific number is always equal to 0. So we're essentially adding 0 to our original probability, so we're not actually changing it. But if I combine these two events, that's the probability that y is less than or equal to 3, which is now, by definition, the CDF of our random variable evaluated at 3. So similar to the, oops, that wasn't what I meant to do. Similar to the previous example, we can now use the CDF function available in R in order to answer our question. But one key detail that we have to be careful of, there are different parameterizations of distributions. And so if we type in px, it's going to give us more information about the exponential distribution. And if we look here, it says that the density is equal to, that the exponential distribution with rate lambda has density equal to lambda e to the negative lambda x. If we compare that to the parameterization in our book, so R's version is lambda e to the negative lambda x, and the book parameterizes it as 1 over beta e to the negative x over beta, to use the same symbol for the random variable x. And so you can see that the way that R parameterizes it is 1 over how we parameterize it. So when we have a rate of, or when we have beta equal to 2 in R, using R parameterization, that means that lambda is equal, so lambda is equal to 1 over beta. So if beta is equal to 2 in our example, that means that lambda is equal to 1/2. So we go to R, we use P because P stands for probability, or CDF. So Px, and the upper bound, or the value that we want for our CDF, is the value 3, and a rate is equal to 1/2. So the CDF evaluated at 3 for our distribution is equal to 0.78, or approximately 0.78. The second question that we wanted to answer is, what's the probability that y is between 1 and 3? And so to answer this question, we'll rewrite it as the probability that y is greater than 1 but less than or equal to 3, which is the same, well, maybe make this very specific. That's the same thing as the probability, as the original probability plus the probability that y is equal to 3, since the probability that y is equal to 3 is equal to 0. But now, if we combine that, that's the probability that y is greater than 1 and less than or equal to 3, which is the probability that y is less than or equal to 3 minus the probability that y is less than or equal to 1. But now we've written the original probability in terms of CDF functions, f of 3 minus f of 1, which is easily, whose values are easily obtained using R. So we go back to R, and we'll type the same thing as before, except for now we subtract from that Px evaluated at 1, rate equals 1/2, and our probability is equal to 0.383. So the key detail with this example was once again translating the original problem into a problem that was easily solved using R. So for the third example, we're going to look at a normal random variable that has a mean of 10 and a standard deviation of 5. And we want to answer 3 questions. What's the probability that y is less than 16? What's the probability that y is between 8 and 13? And what's the probability that y is greater than 13? So as we did in the previous examples, the first thing that we want to do is write the information. So the standard notation for a normal random variable is that y tilde, so this symbol right here means distributed as, and we use the symbol n to specify a normal distribution. And we put mu first, and then the variance, sigma squared, second, which means that in our current example, y has a normal distribution with mean of 10 and a variance of 5 squared, or in other words, it's a normal 10, 25 random variable. And the first question that we want to answer is, what's the probability that y is less than 16? Well, similar to the previous examples, that's the same as the probability that y is less than 16 plus the probability that y is equal to 16. Since for a continuous random variable, the probability that it equals a specific value is always equal to 0. So combining that together, that's the probability that y is less than or equal to 16, which is just the CDF of our random variable evaluated at 16. And similar to the previous examples, we're going to use a p function because p stands for probability, or CDF. So what we want to do here is we want to go to R, and we want to make sure that we know how this distribution is parameterized. So we type question mark p norm, and we see here that the distribution is parameterized in terms of its mean and standard deviation, not the variance. So the book notation and R's notation is once again a little different. So we want to find the CDF of our normal distribution. We want to evaluate it at 16. The mean is equal to 10, and the standard deviation is equal to 5. So the answer to the first question is about 0.885. For our second question, we want to find the probability that our random variable is between 8 and 13. And if we add 0 to that in a fancy way, right, so we add the probability that y is equal to 13, since that's equal to 0, we get the probability that y is greater than 8 and less than or equal to 13, which can be re-expressed as a probability that y is less than or equal to 13 minus the probability that y is less than or equal to 8, which is just the CDF of our random variable evaluated at 13 minus the CDF of a random variable evaluated at 8. So now we can go back to R and quickly calculate those two probabilities. So if I hit the up arrow on my keyboard, that brings up the previous command, and I can just quickly change that. And now I want to subtract CDF of our normal random variable evaluated at 8 with a mean of 10 and a standard deviation of 5. So the answer to my second question here is about 0.381. And lastly, we wanted to find the probability that y is greater than 13. And using the complement rule in probability, that's 1 minus the probability that y is less than or equal to 13. But the second part of that equality, or that expression, is just the CDF function of our random variable evaluated at 13. So we want 1 minus the CDF evaluated at 13. So going back to R, we want 1 minus the CDF function evaluated at 13 with a mean of 10 and a standard deviation of 5. And so the answer to my last problem here is about 0.274. So we've worked through several problems now about how to calculate probabilities quickly and easily using R. So another property of random variables that is very important is the expected value or mean of the random variable. And the expected value is really just sort of a weighted average. So it takes the likelihood of an event, it takes an event, multiplies it by how likely it is to occur, and then we sum or integrate over all the possible outcomes of our random variable. Which means that if y is discrete, the expected value is simply the sum of each possible value of y multiplied by its probability. And if we are looking at a continuous random variable, it is the integral between negative infinity or infinity of each possible value of our random variable multiplied by its associated density, assuming that the sum and the integral are well defined. It's going to be one or the other. So that's how you calculate the expected value of a random variable. A theorem related to expected value is that if you want to define the expected value of a function of a random variable, you can use the exact same formulas that we saw on the previous slide, except that you replace y with a function of y. But the expected value, the calculation of the expected value works the same way whether it's a discrete or continuous random variable. And a specific example of the expected value of a function is in fact the variance. So the variance of a random variable y, which is denoted by either v of y or sigma squared of y, is given by the sum of each possible value of y minus its mean squared multiplied by the probability if y is discrete, or if we're talking about a continuous random variable, we take y minus its mean squared, multiply it by the density, and integrate between negative infinity and positive infinity. So in this case, our function g of y for the variance is that g of y is equal to y minus the expected value of y squared. So the variance is really just a special case of the expected value when the function g is equal to y minus the expected value of y squared. And related to the variance is the standard deviation, which is simply the square root of the variance. So naturally, because we denote the variance by sigma squared of y, the standard deviation is denoted by sigma of y. And so as I've already mentioned, in fact, the variance of y is really just the expected value of a function, and that function is the square of y minus the mean of y. But you can actually re-express this expected value as the expected value of y squared. So of y squared, you take the expected value minus the expected value of y quantity squared. This is not too difficult to show, but it's often much simpler to calculate the variance in this method, using this method, as opposed to calculating it using the definition. And the mean and variance of many of the common statistical distributions are provided in the back of the book or in the table of common statistical distributions that is provided as a supplement for this class. So some theorems related to expected value. Let c be a constant, let g of y, gy1, g1y, etc. be functions of a random variable y. The properties, or the theorem, states that 1. The expected value of a constant c is equal to c. So the expected value of a constant is a constant. 2. The expected value of a constant multiplied by a function of y is the same as pulling the constant out and then simply calculate and multiplying that by the expected value of the function of y. The third property is that if you have the expected value of a sum, that's the same as the sum of the expected values. And this third rule right here is actually an extremely useful and frequently used rule in statistics. The expected value of a sum is the sum of the expected values. Lastly, if you have a constant multiplied by a random variable y, the variance of that constant multiplied by y is the same as if you pull the constant out, square it, and then multiply that by the variance of y by itself. So we're not going to prove these at this time. These are likely to be homework questions, actually. But you can demonstrate each of these in a fairly simple fashion. So we've already talked about quantiles and the fact that quantiles are commonly of interest. And there's sort of a standard notation that's used in this book for talking about quantiles. So the first symbol, For example, we might have quantiles denoted by Z alpha, T alpha, F alpha, chi-squared alpha, etc. And the first symbol is going to represent the distribution under consideration. So Z stands for standard normal, T stands for T, F stands for F distribution, etc. And alpha represents the area in the upper tail of the distribution as a whole, which means that Z of alpha is actually the 1 minus alpha quantile of the distribution. So unfortunately, the book uses a notation that, in my opinion, is more confusing than it has to be. But, for example, Z of 0.10 is actually the 0.9 quantile of the standard normal distribution. So you might be tempted to think that this is, in fact, the 0.1 quantile, but it's actually, so if alpha is 0.1, then 1 minus alpha is 0.9. So Z of 0.1 represents the 0.9 quantile of the standard normal. T of 0.025 represents the 0.975 quantile of a T distribution, etc. So some practice that we can use for, so we should practice this. So for example, we might want to calculate Z of 0.025. We might want to calculate T of 0.2 for a T random variable with 10 degrees of freedom. We might want to calculate the 0.95 quantile of an F distribution having 4 numerator degrees of freedom and 8 denominator degrees of freedom. So I'm just going to minimize this actually. We'll go over to R and calculate this. Oh, maybe it might not let me here. All right. So Z of 0.025. So Z stands for standard normal distribution, and alpha is equal to 0.025, which means that we want the 0.975 quantile of our standard normal distribution. So what that means is that, so actually I guess what I would recommend is pause this, see if you can't solve these on your own, and then we'll come back together. All right, so hopefully you're able to struggle through that and get the correct answer, but if not, then we'll talk about it right now. So you may remember from the previous discussion of the functions in R that the quantile functions always start with the letter Q. So Z stands for standard normal, which means a normal distribution with mean 0 and variance 1. We want the 0.975 quantile of that distribution. So we want to use Q norm, and we want the 0.975 quantile, and then the mean of our normal is 0, and the standard deviation is 1. So essentially that quantile is 1.96. However, by default, R assumes that you're dealing with a standard normal distribution. So if you don't tell it the mean and standard deviation, it will assume the mean is 0 and the standard deviation is 1. So you can simply put Q norm of 0.975 to save yourself a little bit of time, and you get the same answer. So for this second question right here, we want T of 0.2 for a T random variable with 10 degrees of freedom. So we're dealing with the T distribution, and alpha equal to 0.2 means that we want the 0.8 quantile of that distribution. So we once again are going to use a Q function for quantile. We want the quantile of the T distribution. We want the 0.8 quantile, and then the degrees of freedom is going to be equal to 10. So the answer to the second question here, this is not going to work out very well here. So the answer to the second question here, the 0.8 quantile of a T distribution with 10 degrees of freedom is about 0.88. Lastly here, we want F of 0.05, where F is F stands for an F random variable, and we'll have 4 numerator degrees of freedom and 8 denominator degrees of freedom. So because alpha is equal to 0.05, 1 minus alpha is 0.95, which means that we actually want the 0.95 quantile of our F random variable. And since we want that quantile, we once again use the Q function, but now we use F, standing for the F distribution. We want the 0.95 quantile, and the numerator degrees of freedom is equal to 4. The denominator degrees of freedom was equal to 8, I believe. And so the quantile in question is about 3.84. So using R, we can easily calculate quantiles for the common statistical distributions. We simply need to know how the different distributions are parameterized. So let's do some practice now of calculating the expected value and the variance for a couple of distributions. So suppose you have an exponential random variable with scale parameter beta equal to 2. The first question is, what is the expected value of y? What's the variance? Then the next one is, what is the variance of y? And we also want to find what's the expected value of 4y, and what's the variance of 4y. So I want you guys to pause this lecture, and then in whatever way you want to, see if you can calculate the expected value of a random variable and the variance of a random variable, either using the definition or using some simpler mechanism. Well, I hope your endeavor was successful. Let's see if we can answer this question together. So, once again, let's write the information that we know. So we know that our random variable y has an exponential distribution with a scale parameter beta equal to 2. We want to find the expected value of y. Well, since this is a continuous random variable, by definition, this would be the integral from negative infinity to infinity of y times the density 1/2 e to the negative y over 2 dy. But because the density is defined to be 0, whenever, for impossible values of y, this can be simplified to the integral between 0 and infinity of y times 1/2 e to the negative y over 2 dy. So this integral is actually solvable using integration by parts, and you can show off your calculus power by doing so, but that's actually a lot more difficult than it needs to be. So if you look at the table of common distributions that's applied for this class, you'll see that the exponential distribution is one of the distributions that is listed by default. And so if you look at the exponential distribution, you will see that for the parameterization that we're using, the mean is just beta. The variance is just beta squared. And so without doing any integration whatsoever, we know, using the table of common statistical distributions, that the expected value of this particular random variable, since beta is equal to 2, is equal to beta, which is 2. So the expected value of this random variable is equal to 2. Similarly, the variance of our random variable is going to be equal to beta squared, which in this case is 4. And so we didn't have to do any integration to do that. So this is much straightforward, much simpler. Use the information that you have at your disposal. So the expected value of y is 2, the variance of y is 4. We also wanted to calculate the expected value of 4y. And using that theorem that we saw earlier, we can pull out the constant. And so we get 4 times the expected value of y. But we know that the expected value of y is equal to 2. And so the expected value of 4y is just 8. Similarly, we want to find the variance of 4y. And once again, we can pull out the constant, but because we're dealing with the variance, we have to square it. And we multiply the square of the constant by the variance of y, so we get 16 times 4, which is equal to 64. So the variance of 4y is equal to 64. And so, looking at this example, what initially could have been a pretty annoying or pretty tedious example by trying to integrate out our expected value by definition, which sometimes we'll have to do. Instead, we used the table of common statistical distributions. We used the fact that we knew the mean and the variance for the exponential distribution. That allowed us to solve this problem in a much quicker fashion. So, related to that, let's find the expected value and variance of random variables with the following distributions. So a binomial random variable with n equal to 21 and p equal to 1/3, a Poisson random variable with lambda equal to 3, a chi-square random variable with nu equal to 10, and a gamma random variable with alpha equal to 2 and beta equals 6. So please pause this lecture and then pull out the table of common statistical distributions and see if you can answer these questions on your own. All right, so let's pull it back together and see if we can't answer these questions. So our first random variable was a binomial random variable with n equal to 7, I believe. Equal 21, sorry. So n is equal to 21, and the probability of success is equal to 1/3. So the mean, in that case, expected value of y, using our table of common statistical distributions, is just np, which in this case is 21 times 1/3, which is equal to 7. Similarly, the variance is going to be npq, which is the same thing as np times 1 minus p, which is 21 times 1/3 times 2/3, which is going to equal 14/3 using our previous work. So that is the mean and the variance of our first random variable under consideration. For the second random variable, the distribution was Poisson with lambda equal to 3. And if we look at our table of common statistical distributions for a Poisson random variable, the mean is just equal to lambda. So in this case, the expected value of y is just lambda, which is equal to 3. And similarly, the variance is also equal to lambda, which is equal to 3. So the Poisson distribution has, for a Poisson random variable, the mean and variance are going to be equal. So for the third random variable, we had a chi-squared random variable with 10 degrees of freedom. And if we look at our table of common statistical distributions, we see that for a chi-squared random variable, the expected value of the random variable is just its degrees of freedom, which in this case is 10. And the variance is 2 times the degrees of freedom, which in this case is 20. And for the last example, we had a gamma random variable. The parameter alpha was equal to 2, and the parameter beta was equal to 6. So the expected value of our random variable is simply going to be alpha beta, which in this case is 2 times 6 equal to 12. And the variance is going to be alpha beta squared, which in this case is 2 times 6 squared. So we get 2 times 36, which equals 72. So we were able to calculate the mean and variance of the mini distributions in a fairly straightforward manner using the table of common statistical distributions. Well, that's the end of this little review of chapters 3 and 4. If you have any questions, please let me know. Otherwise, I look forward to seeing you all on Tuesday.